Right, well, hello and welcome to our first Bite-Sized Corrosion series for 2025. And once again, we're going to be breaking down an aspect of corrosion-related information into what are hopefully interesting and informative, palatable nuggets of information. I'm Vanessa Seeley-Fisher, and it is my honor to host today's conversation. We hope that you will leave us today having learned something new and eager to continue your journey in understanding corrosion a little bit more and applying this in your own corrosion experience. Now, in this series, we're going to be exploring some what I've termed high-tech coatings, trying to get to grips with what they are, what they can and cannot do, where they can and cannot be used, and what to look out for along the way. So whether you're a professional who's working in the high-tech coatings industry daily, or this is a subject which perhaps like me, you know fairly little about, I'm sure you'll find valuable insights during today's discussion. So today we are kicking off our discussion by tackling this very broad topic of epoxy coatings under the high-tech coating banner. And joining me today, I'm delighted to have Mark Stone. Mark has just stepped into a new role at Stoncor and has very bravely agreed to talk to us. But he's no stranger to epoxies. With a chemistry degree and years of developing epoxy formulations, he's very well versed on the topic. So welcome, Mark. Thank you for joining us.
Thanks for having me, Vanessa.
That's a pleasure. Now, Mark, the word epoxy conjures up so many things to so many people. I think it would be helpful in today's session to describe what we are going to be meaning today when we talk about epoxies.
So I always think about how to explain this to people, and I think the best way to do it is to break it into two simple words. So an epoxy is a thermoset polymer. And to break this further down, I've actually got the definitions of what thermoset means and what a polymer is, so we can better understand what an epoxy is. So a thermoset means a material that hardens permanently after one application of heat or pressure. Another definition of it is a thermoset polymer forms by the reaction of two or more components. Okay, so if we break that down, we're basically saying epoxy is a two-component material that undergoes a one-way reaction that can't be reversed. It gives off an exothermic, that's where the thermo comes in, it gives off a bit of heat, and it forms a new material after this whole reaction. What is that material? That's where the second word comes in, the polymer. So the simplest way to think of a polymer is to think of a plastic. That's what we all think when we hear the word polymer. And in essence, an epoxy is a type of plastic. It's a long chain molecule. It's got reoccurring pieces in that molecule called monomers. And that's basically what an epoxy is, mixing these two components to form this long chain molecule that's very strong. And it's useful in applications such as coatings, adhesives, waterproofing, all those kinds of things. So in essence, that is what an epoxy is.
Thank you. I think that's a really clear explanation and will really help us, but it leaves me with a question. And that is, you've said there are two components, two parts of it, because it's a polymer. But when I go to the local hardware store, sometimes I have a choice between a twin pack, which I suppose is the two components, and the single pack system. So how is this an option and how are they different? Why are they different?
Okay, so in your shops, you'll get these two different things, the single packs and the dual packs. And the glaring difference between them, apart from the number of components, is the curing mechanism. So we really need to ask ourselves, how do these products get hard at the end of the day? You've got these liquids in your tins, how do they get hard? So we've already spoken about how an epoxy gets hard. You've got your part A, which is normally your epoxide resin, and you've got your part B, which is normally a nitrogen-containing group, such as a amide, polyamide, that kind of thing. Those react, thermoset polymer, we got that. So a single pack product dries in a different way. This is normally an air drying product. You do get exceptions where it's water cured and stuff like that, but we won't get into that. We're talking mainly about your builder's warehouse single pack paints. And what these are air drying. So you're basically taking the product out of the tin, painting it onto your surface, and you're creating this lower volume of material with this larger surface area. So if you can picture on a rainy day, you've got a puddle outside, that's exactly the same thing. You've got this big surface area of puddle, and that quickly evaporates once the rain's dry, and you lose your puddle. Same thing with a single pack paint, normally like an acrylic or something. So these are normally solid resins that are dissolved in a solvent, and these solvents evaporate off and leave your solid resin there with all your additives and everything in it. The chemical reaction of an epoxy makes it a lot stronger. You've got an actual chemical reaction happening. You're making bigger long chain molecules that form this network, making it very strong. Whereas your single pack paints and stuff like that tend to be a lot weaker. You've got, if you can picture it like little springs, that's kind of the shape of your acrylic resin. And when the solvent evaporates off, these springs kind of intertwine together, and that's what you're left with on the surface. So it's a lot easier to break apart springs than to break apart a polymer. So that's the glaring difference, is that your epoxy is going to be more chemical resistant, abrasion resistant, temperature resistant. It's going to last a lot longer. It can also go on a lot thicker because you're not relying on that solvent evaporation.
The drying.
Your single packs are basically, the advantages of it is it's easy to use and it's cheaper. People don't have to think about mixing a part A and part B. It's just take it out the tin and paint.
So when we're talking high-tech coatings, we generally are not talking about a single pack system. And when we're talking about epoxies, we're always talking about a two-component system. By definition, it's a hardener or a curative plus your resin. Am I correct in my understanding?
Yes, correct.
Okay, so if we're looking at high-tech coatings, why would I want to choose an epoxy? What are some of the benefits they would bring to our challenge that we need a high-tech coating for?
I think that the best way for me to explain the advantage of an epoxy would be to speak about the industry I'm involved in. So I'm primarily involved with protecting steel on our Carboline range. And the biggest problem with steel is that it rusts. So your rust is basically water and oxygen attacking your metal. This forms a mini battery where you've got a cathodic side and anodic side. And on the anodic side, it loses electrons and rusts. What an epoxy does is the best way to stop the rust is to separate those components needed for the rust. So you're separating your metal from your oxygen and water by putting an epoxy layer down the middle. So that's called barrier protection. And that's the biggest advantage of an epoxy, is it creates this almost impermeable barrier that protects your steel from getting into contact with water and oxygen and stuff like that.
So if we're thinking about epoxies as barriers, they're going to be going on as the first layer of coating, I would imagine, very often. So maybe as a primer.
Oftentimes, there is another case where you want a bit of added protection. So on structures like big bridges and stuff that go up, you want that added protection. You don't want any risk on that structure. So then you'd start looking at primers, which is what we have called corrosion inhibitors. And you can put those into your primer and onto your surface, which protects even further. An interesting thing with that is you've got a table called the galvanic series. Mm-hmm. And that, as I mentioned, with cathodic and anodic metals, you've got your list from most cathodic to most anodic. So what's often used as a corrosion inhibitor is zinc. Oh. And zinc is pretty much the most anodic metal you're going to get. So we paint that on as the primer for structures such as bridges. And what that does is you've now got two metals touching. You've got your steel and your zinc touching. And your zinc will preferentially rust before the steel. So you've put that on, and then you put your epoxy on as the barrier coat. And what that does is, if you ever have any issues where a piece of your epoxy has been gouged out and you can see your steel underneath there, that steel is not going to rust straight away. You've exposed your zinc now to the atmosphere, and your zinc will now preferentially rust instead of your steel. So yeah, epoxy often primer, but in certain cases you can get in corrosion inhibitors that go on first.
Okay, so the point of these high-tech coatings using an epoxy is primarily, in the steel industry anyway, is for corrosion protection, which is a good thing because this is bite-sized corrosion and not something else. And are there different classes of epoxies or types of epoxies with specific attributes that you might choose to use based presumably on some group within the epoxy formulation?
I mean, you've got your two components that we've mentioned. So your first component would be your epoxide resin, and your second component would be your hardener or your curing agent. On each side of the scale, you can change things around and play with them to get bigger advantages or more preferable abilities of the coating, for lack of a better word. So on your part A with your epoxide resin, you get a bis A resin, bisphenol A resin. That is more your general purpose resin for primers, things like that. You also get what's called a bisphenol F resin. That is more for chemical resistance. It's a smaller molecule than the bis A, so you form tighter networks in that 3D network. Right. So more impermeable, better chemical resistance and water resistance and all that. And you also get a resin called an overlap resin, which has more functional groups within it. So again, you're building that 3D structure, you've got more functional groups to build a more dense network, also for chemical resistance. Then on the hardness side is where you can really play. I'm talking it from our side of designing these epoxies. But even when deciding which epoxy to use, we would look at these kind of things. So you've got these groups. I won't go into depth on the groups because within each group, you've got many options of what you could use as your hardener. But for an overview, you've got amines. Amines they've got great chemical resistance. They're fast curing. Of course, all these things have drawbacks, so the drawback for amines would be that it is very sensitive to moisture. So you could get what's called blush on your epoxy. There's another class called polyamides. Polyamides are also chemically resistant, not as chemically resistant as the amines, but then you've got advantages such as low temperature cure and flexibility. So if you need a bit of flexibility, or more importantly, if you need to be able to cure in lower temperatures, you coating pipes underground, or you work in a cold country, then you'd use a polyamide. And then you've got another group called your phenalkylamines. Phenalkylamines extremely chemically resistant, fast curing. Their biggest advantage is that they are not as sensitive to moisture. So any application where it's going to be humid, or if you're coating a pipe that's in situ at the moment, then that's what you would use. An interesting thing is also that you can play with these Part B components. So you can have a polyamide with a phenalkylamine to get the best of both worlds. Your possibilities are endless with what you can choose in your epoxies. Yeah.
The difficulty of that is you need a laboratory to do lots of playing with. And sure. I think very often the engineers end up with little time to make the decisions, and we maybe don't customize as much as we could. I just was listening to your comment about the moisture sensitivity. So the amides, you didn't highlight that as being a concern, but is a high level of moisture in general with epoxy something to caution against during the application? Would that be sort of a good rule of thumb?
So the amines are quite sensitive to the moisture.
But the amides less so.
Yeah. You got some that are less sensitive, some that are more sensitive. It's normally your smaller molecules that are very reactive that and start reacting with other things if you're not careful. Yeah.
So in a previous Bite-Sized Corrosion series on coatings, we really highlighted the importance of surface preparation. And I'm not going to ask you to say there's no surface preparation required. Of course there is. But do epoxies really need the high levels of cleanliness like SA2.5, SA3? Or are they a little bit more surface tolerant? Or are you going to tell me that we can design it so that it can be?
Yeah, again, you get your curatives that are more surface tolerant. But in general, surface preparation is 80% of your battle. If you're painting a surface, whether it be with an epoxy, polyurethane, acrylic, whatever it may be, you're not getting a chemical bond from, I'll use steel again, you're not getting a chemical bond from your coating to your steel. So what you're relying on is a mechanical bond. So when preparing steel, for instance, there's kind of like 3 things you need to take note of. And this is actually in general for concrete, whatever you painting, you need 3 things, which is the surface needs to be clean. Mm-hmm. The surface needs to be free of any grease or oils or anything like that, or soluble salts, anything like that that can affect your bond. And then the third thing is you need a profile. So with steel, we work to, like you've mentioned, SA2, SA2.5, all of that. So yeah, that is generally what we work to, the level of cleanliness. It's a visual standard. So you are blasting your steel. It's always preferable to blast it. The ST standard for hand tool cleaning and all that, but always preferable to blast it. Yeah, the SA goes up to 3. So SA3 is your clean white metal. And again, you're comparing that to a picture standard to make sure that you're getting the correct bond for your epoxy. Another thing importantly to note is that if you've blasted your steel to whatever surface standard you're trying to get it to, just because you've blasted it today doesn't mean that blast is still going to be there in 3-4 days. It's quite important to get your coatings on quite soon after blasting. Otherwise, you get all those contaminants and stuff sitting back onto the surface, and clean steel rusts quickly. Yeah.
Yes. Yeah, the cleaner it is, the more it seems to attract the dirt and the rust. That's always the way. A little bit earlier, you made a comment about the thickness of the coatings, and one of the challenges that I've encountered is that if your profile is too deep or the number is too high, you're going to get breakthrough through the thinner coatings. What are the kinds of thicknesses that epoxies are generally applied to in a single pass? And then the second half of that is, can you build them up?
Yeah. So epoxies generally, you're looking at about 100, 125, 150 microns per coat, especially with primers. That's to correctly, like you said, cover the surface profile. If you think of it on a microscopic level, you don't want those peaks of the steel sticking out the top because they will rust. So yeah, in general, about 125 microns per coat, and normally 2 coats to make sure you've covered everything and haven't missed a spot.
Just for our audience, when you get those peaks breaking through, it's often termed measle corrosion, and it actually looks like the surface has got measles, which I guess is why it got called that. But it is real. It needs to be coated properly to make sure you've covered all of those peaks when we look at our coatings. In terms of overcoating epoxies, are they fairly amenable to having other coatings or other epoxies applied over them, or do they need special kind of intercoat treatment?
Generally, they're quite amenable. We overcoat epoxies with other epoxies or polyurethanes or sometimes acrylics. Generally, you want to coat your epoxy before it's fully cured again, so you can get a kind of a chemical bond between like your polyurethane and your epoxy or your second coat of epoxy. Thereafter, when it's fully cured and super hard, then you'd need to create a mechanical bond, which we've spoken about. So you need to sand your surface and then paint onto that.
Now, when you say fully cured, I know in the coatings industry, the term cure and my sense of cure might be different. Now, I'm going to use a very female example of nail polish. You apply it and you think it's dry when you touch it, but if you bang it against something, it's still soft and it smudges. So that's why I don't wear nail polish. But is it the same with these coatings that as you apply it, there's going to be a level of touch dry, but curing might take quite a lot longer?
Yeah, for sure. If you can picture it on like a microscopic level, all those molecules and stuff are still moving around and bonding with each other and all that. So just because it's touch dry doesn't mean it's fully cured. So normally with epoxies, it's about 7 days for it's fully cured.
So there's time is required for these things. Now we've
Especially
spoken
when you're looking at some critical applications like tank linings and stuff like that, then you really want that stuff properly cured before exposing it to the chemicals it's designed for.
Exactly. And one of the challenges of that is often they're done as maintenance coatings. So there's that pressure to get it back in service yesterday, and know that it still needs a week to cure. It is a real challenge. We've spoken, Mark, about some of the general uses and the ease of using epoxies, but I'm guessing like any other coating, the epoxy is not the perfect solution to every problem. Are there some drawbacks that we should be aware of when we talk about epoxies, things that we should be cognizant of that they might not be a suitable solution in our particular situation?
Yeah, so epoxies are extremely versatile. There's not many things that an epoxy can't be a solution for. But one thing an epoxy really struggles with is UV. So any UV exposure kind of tends to yellow the coating. Or another thing that happens is that the top of an epoxy will chalk. So the UV, in an epoxy, there's many like aromatic bonds, and I don't know if this makes sense, but the UV breaks those aromatic bonds down, and that's what's called chalking. You'll get almost like, it looks like someone's colored over your surface with some chalk. And that's basically the degradation of that top layer. It doesn't diminish from the performance of the epoxy, but it just doesn't look great. So often you want to top coat that.
Okay, so it's an aesthetic challenge primarily rather than Hypothetically, though, could you get the situation where exposure to weather has caused such deterioration that actually the epoxy fails?
I think for that to happen, you'd need firstly a lot of time, so many years for that to happen. And secondly, you'd need a scenario where you've broken down that layer, something like I don't know if rain could even take it off, but something has taken that layer off and you've exposed the next layer for the UV to attack. That chalking layer kind of protects the layers underneath it.
Right. Okay. So a little bit like the function of the zinc in the primer, that it's there as a protection. And
Yes,
then
yeah.
even as it gets used, it also can discolor if you've just applied that. That's so interesting. And in terms of use of epoxies in the more decorative or aesthetic market, the above ground applications, are there color constraints? I mean, you've mentioned it might yellow, but are there color restrictions in terms of what colors these coatings can be generated or manufactured in? Or they're quite broad?
No, it's quite broad. I'd say you can do your epoxy in pretty much whatever color you'd like. But yeah, if it's going to be above ground, generally you'd want to top coat the epoxy to make sure it looks beautiful for years. So, normally you would top coat an epoxy with polyurethane, which is a lot more UV stable. It's got better color retention and it's not going to yellow. So the finish you put onto that surface is going to be the finish you're going to look at in a few years' time if you top coat it with a polyurethane. There's cheaper options as well. Of course, you could put an acrylic and stuff like that, but yeah, generally a polyurethane will last you one of the longest.
Great. Well, thank you, Mark. And thank you also because you've just given us an introduction for tomorrow's session. So I think it's been really interesting today to learn a little bit more about epoxies, just their general usefulness, but also some of their constraints. And tomorrow, as Mark has alluded to, we're going to look a little bit further. And in fact, tomorrow we're going to be discussing polyurethanes. So in closing, I just want to thank you, Mark, for taking time out of your day. We wish you well in your new position. And I've no doubt we'll be chatting with you again. And I trust to all of our audience that you found today of value and that you'll leave us today feeling that you've benefited from today's conversation. Thank you.